Hello students, I welcome you all to my session on bonding in coordination compounds. In this session, I will be discussing and explaining the bonding that is present in the complex ions. There are different theories to explain the bonding. One is valence bond approach. You have crystal field theory, ligand field theory, and also molecular orbital theory. But in this session, we will confine ourselves only to the first two, that is the valence bond approach and the crystal field theory. To explain the valence bond approach to bonding in complex ions, I will take the example of FeCN6 4- ion. This is an anionic complex, and you can also calculate the charge on the ion here, which is +2, isn't it? You can do that, and we call it hexacyanoferrate 2. That is the name of the complex ion according to IUPAC nomenclature. Let me begin with the electronic configuration of the iron atom with 26 electrons. We can write it as Ar 4s2 3d 6. You know 4s is filled before 3d. So the electronic configuration of the iron atom is thus. But I have written 4s after 3d because, as you know, while removing the electrons, they are removed only from the outermost orbital. So the electrons from 4s will go away first. So I have written it in this order. For the electronic configuration of the Fe2+, it will be Ar with 6 electrons in 3d, and as we said, 2 electrons have gone away from the 4s orbital, so the 4s will be vacant. Now this hexacyanoferrate complex ion has 6 ligands. It is hexa-coordinated, having 6 ligands. For a hexa-coordinated complex, the shape is octahedron. Octahedron is a symmetrical shape. Now to form an octahedron which is symmetrical, you need 6 hybrid orbitals. That is, the 6 orbitals have to be mixed, and then 6 equivalent hybrid orbitals are to be produced from them. Now, though we have not shown, the 4p orbitals and 4d orbitals are also present, which are vacant. Okay. I'm sorry, this is 4p and this is 4d. Now, how can we get 6 hybrid orbitals? We can take the vacant 4s, 3 4p and 2 4d and hybridize them to get 6 sp3d2 hybrid orbitals. These are called sp3d2 because we have taken 1 4s, 3 4p and 2 4d in the same order as spd, so we call them sp3d2 hybrid orbitals. The other possibility is we will take 2 orbitals of the 3d level. How do we take them? There are electrons present in all, but you know we can vacate the orbitals by pairing up the electrons. The 6 electrons can be present as 3 pairs, and 2 orbitals of 3d can be vacated, and there you have 4s and 4p. So we can form 6 hybrid orbitals using 2 numbers of 3d orbitals, 1 number of 4s orbital and 3 numbers of 4p orbitals. In this case, we will call it D2sp3 following the order in which the orbitals are present. So D2sp3 is the hybridization present in the second case. Since we have taken the outer d orbital, that is 4d orbital, this is called an outer orbital complex, and this can be called as inner orbital complex. Okay, which one is correct? For that, we we use the magnetic data. The experimental magnetic data says that this complex is diamagnetic. That means it is not having any effect in a magnetic field. So this is said to be, it's not affected by a magnetic field. So this is said to be a diamagnetic complex. So you understand that there are no unpaired electrons. You know, normally paramagnetism is associated with the presence of unpaired electrons. And if something is diamagnetic, there are no unpaired electrons in them. So we have to take the second case where there are no unpaired electrons. In the first case of sp3d2 hybridization, you have 4 unpaired electrons. So it should be paramagnetic. Since the experimental data shows that it is diamagnetic, it is a case of d2sp3 hybridization. Right. So what are the facts that we will write about this complex? Now you see on the slide that it is an inner orbital complex, diamagnetic, and having an octahedral geometry. So this is how we explain the bonding that is present in a complex ion. I will take up another example now. The example is COF63-, which is hexafluoro cobaltate 3 complex. Hexafluoro cobaltate 3 ion. The charge on the cobalt is +3, isn't it? Cobalt is +3 here. So what is the first step? We write the electronic configuration of the cobalt atom with 27 electrons. Then we remove 3 electrons, first 2 from the 4s and 1 from the 3d to get the electronic configuration of the cobalt 3+ ion. So please pause here and try to do it on your own. If you have understood what I explained, there should be no problem in writing the electronic configuration of the cobalt 3+ ion in the complex. Then I give you one more data, which is that the complex is paramagnetic. That should help you in arriving at the type of hybridization. Please go ahead and do it on your own and then check up with what is done here. Look at the electronic configuration of the cobalt atom and the cobalt ion here, given here. And as per the data I gave you regarding the magnetic character of the complex ion, it is paramagnetic. I suppose you will be able to choose the orbitals for hybridization here. To make it paramagnetic, we should allow the unpaired electrons to remain as it is. Hence, we should involve only the 4s orbital, 4p orbitals and the 4d, 2 of the 4d orbitals for hybridization. So these are the orbitals to be taken for hybridization. It will form sp3d2 hybrid orbitals. 6 orbitals of sp3d2 type, which are equivalent in nature, which are mixed to form, which are used for forming the bond with the ligands. In these 6 vacant hybrid orbitals, I will write them, show them separately as 6 hybrid orbitals in which you have the electron pairs from the ligands located. So what are the details that you can write about this complex ion now? It is an outer orbital complex. Then you know it is paramagnetic. Here we can also write the hybridization, sp3d2 hybridization. Then the shape is octahedral. I suppose it is clear to you. We have taken 2 examples to explain bonding in the octahedral complex. One is the hexacyanoferrate and the other one is hexafluorocobaltate. Both these ions are isoelectronic. What do you mean by isoelectronic? Having the same number of electrons. So both have the same number of electrons, that is 24 electrons. And then in one case, since it happens to be a diamagnetic ion, we have paired up the electrons, unpaired electrons, vacated the 3d orbitals and formed the inner orbital complex. And the second one, it is paramagnetic, hence we left the unpaired electrons as they are and then took the vacant orbitals for hybridization to form the outer orbital complex. I suppose I have made myself clear here. We will take up the tetra coordinated complex ion next. To explain bonding in tetra coordinated complexes, I will take the example of tetracyanonickelate. This is 2 minus tetracyanonickelate ion. In this, nickel is in 2+ state. So to begin with, we will have to write the electronic configuration of the nickel 2+ ion. That will be like this. Nickel atom has 28 electrons. So Ni2+ has 26 electrons. This will have 8 electrons in the 3d orbital and 4s orbital is empty. Of course, we have the 4p orbitals also. This is 3d with 8 electrons, 4s and 4p. Now, when there are 4 ligands, there are 2 geometries possible. One is the tetrahedral geometry and the other is the square planar geometry. And as you all know, tetrahedron is always associated with sp3 hybridization and square planar geometry is associated with dsp2 hybridization. And to determine which of the 2 structures is possessed by the given complex ion, we have to have some data. Here, as usual, the magnetic data comes to our help. And this is a diamagnetic complex. And once you say it is diamagnetic, you can immediately conclude that there are no unpaired electrons. So what should be the next step? We have to pair up these 2 electrons. So we will have one d orbital vacant there. The other 4 have electron pairs. And one of the 3d orbital is vacant. With this we will combine with an empty 4s orbital and the 2 of the 4p orbitals like this, and we will have 4 dsp2 hybrid orbitals. dsp2 hybrid orbitals. In these vacant orbitals, the electron pairs donated by the ligands are placed. This is how we discuss bonding in the tetra coordinated complexes. So what will be the things that you will have to write when you discuss bonding? One is the given data, that it is diamagnetic. Second is the hybridization, that is it is having dsp2 hybridization in the molecule. And then you have to mention that it has a square planar shape. Okay, so these are the things you will have to mention when you discuss bonding in a complex. Having listened to me so far, if you have understood what I explained, there should be no problem in answering a few questions that I will be giving you right now. Go through the 3 questions given. Try to write the answers on your own and then come back and check with the solutions. In the first question, we start with writing the electronic configuration of this CO3+ ion, and then the complex is given as paramagnetic. So you should leave the unpaired electrons as it is, and so you will have to go for the sp3d2 hybridization. Since it is sp3d2 hybridization, it is an outer orbital complex. And of course, for 6 ligands, it will always be having octahedral shape. So that is the answer for the first question. In the second question, the given ion is tetrachloronickelate 2. So first we write the configuration of the Ni2 plus ion in this, and since it is paramagnetic, we should leave the unpaired electrons, and so the orbitals that are to be taken for hybridization are 4s and 3,4p, sp3 hybridization. When it is sp3 hybridization, obviously the shape is tetrahedral. So you arrive at the geometry this way. The third question, the given ion is tetracyanoplatinate 2 and it is said to be square planar. So, here platinum occurs in the same group as nickel and palladium in the D block. Okay, nickel, palladium, platinum occur as one group, and so Pt2 plus also has D8 configuration like Ni2 plus. We can write the configuration as we normally write for Ni2 plus with 8 electrons in the D orbital and no electrons in the S orbital and P orbital. Of course, it will be 5d, 6s and 6p. And to have the square planar geometry, obviously the hybridization should be dsp2. And so we have to vacate one of the d orbitals, and we do that by pairing up the electrons. So when all the electrons are paired, there are no unpaired electrons. So the number of unpaired electrons is 0. So these are the different ways in which questions can be asked on this topic. That is, you can be asked to discuss bonding in a given complex, or you can be asked to derive the shape of the given complex with the magnetic data given, or you will be asked to find out the number of unpaired electrons when the shape of the complex is given. I suppose it is clear to you. I will discuss the crystal field theory in another session.